Okay, so the next 20 minutes will be about phase contrast MRI. And I will talk about the basic principles in cardiac gating, then how to post-process the data, how to quantify blood flow. Then I will speak about clinical applications and especially errors you need to avoid when doing phase contrast MRI. And then I will say some things about 4D flow MRI, which is my research topic. So phase contrast MRI, you normally get 3 images. There's the magnitude image with the anatomical information. There's the velocity image with, well, of course, the velocity information, that's the phase contrast image. And it also has the information about the direction of the velocity. And this is an aortic valve with the blood flow going up in the ascending aorta, and here the descending aorta with the blood flowing down. And you also can get, if you set the scanner to calculate these images, the modulus image with the velocity information, but without the information about the direction. So everything's bright when there's a fast flow, no matter what direction. And you can do a lot of things with these images. You can get morphology information. So I can say now this is a tricuspid aortic valve, which looks healthy. And we also get velocity information. And we can not only look at it qualitatively, what we often do in 4D flow MRI, we can especially look at it quantitatively. We can measure the flow, we can measure velocities, we can measure or calculate wall shear stress from these values and kinetic energy. So there's a vast amount of data you can get from phase contrast imaging. How do you get that? It all starts with a bipolar gradient. So you apply 2 gradients, they have the same intensity and duration, but a reverse polarity. And they act on the spins in your body, or in your patient's body. So there's the stationary spins, for example, fat or muscle tissue, and the moving spins in your blood cells, so the flowing blood. So this is a vessel and the surrounding tissue. And if you apply the first gradient in flow direction, that's very important, this gradient affects both spins equally. So then you apply the reverse gradient. And since the stationary spin gets the same gradient but with a reverse polarity, the phase shift of this spin is cancelled out and you don't get any signal from that. So that's great. But the moving spin moves along the gradient, so it realizes another gradient and it gets another phase shift that is proportional to its velocity. So that's great. So that's how we measure flow velocity in our non-contrast images. Unfortunately, there always has to be an unfortunately. There's magnetic field inhomogeneities, there's eddy currents and concomitant gradient effects that may affect those two. So it's not ideally as I've shown you, but the basis is the same. So you take this sequence to determine the flow velocity. You take this flow sensitive sequence where the phase shift encoding the velocity depends on the velocity and on other disturbing factors such as magnetic field inhomogeneities. And to get only the velocity, you cannot do a flow sensitive skin that is only dependent on the velocity. But what you can do is doing a flow insensitive scan that doesn't measure the velocity and where the phase shift only depends on the other disturbing factors you want to get rid of. And then, if you do simple maths and subtract both scans, you get the phase images where the signal intensity is directly proportional to the velocity image. That's the phase contrast MRI. And if you add both sequences, you get the magnitude images with anatomical information. So now you've got the image, but you know the heart is beating, there's a cardiac cycle, there's different flow at every time point during the cardiac cycle, and you want to measure that. So what you need cardiac gating. And to acquire images during the cardiac cycle, you divide the cardiac cycle in several time points, in several time intervals. And for each time interval, you measure the reference scan, the flow insensitive scan, and the flow sensitive scan, and you collect your data and put it into K-space. You will not be finished after just one time point because that's very fast. That might be 30 milliseconds or something. So you need to continue collecting your data during other cardiac cycles. And if you're done after several cardiac cycles, you can subtract both images, and then you get the phase contrast and the magnitude data again. And since we're seeing this image more often, you can see the ascending aorta here, and it's a transverse slice through the aorta. So you see the ascending aorta, the descending aorta, and the main pulmonary artery.
Thekla,
Yeah.
can you speak in the microphone with
Sorry.
recording
Oh, sorry. Okay. So you can do cardiac gating in two different ways. So you can do it prospectively or retrospectively. The prospective gating is positive for mild arrhythmia because it's kind of insensitive to that. And you always wait for your R-spike and then you're collecting the data. Unfortunately, since you don't want to collect data in early systole at the end of the cycle, you don't collect the flow data at the late diastole. On the other hand, you can do retrospective gating, and you collect data from the whole cycle, and you bin it just afterwards. That might lead to small inaccuracies due to data interpolation. So now we've got our data. We've got the data for the whole cardiac cycle. What do we do with it? We want to quantify it. And as I said, the gray values encode the velocity. And unfortunately, there's no standardization for the direction. So black or white can mean up or down, depending on the scanner. In this case, white means going up in the ascending aorta, and black means blood flowing down in the descending aorta. So you delineate the contour of the ascending aorta. And if you're doing that at the peak systolic image, you get the peak velocity. If you're doing that for all the images during the cardiac cycle, you get the velocity profile of the aorta with the antegrade and the retrograde flow. And you got loads of other information: stroke volume, regurgitant fraction, peak velocities and flow, and peak pressure gradients. But before you take this data, you need to be aware of one error, the phase offset errors. So if you scan a static phantom in your MR scanner, the MR scanner will measure flow, although there's no flow. Just a little bit of flow. This is due to concomitant gradients and eddy currents. If you want to get rid of this phase offset error, you can measure flow in a static tissue that is just near to your vessel. So if you want to measure flow in the ascending aorta, we delineate a contour in the pectoralis muscle, and then you get a very slow flow, and you subtract that from the flow in your ascending aorta, and then you get the proper values. You can also do it with a static phantom bottle afterwards and just measure the flow in the static phantom, but that's very time consuming, so we do it with the ROI in our measurement volume. So now we've got all that data. What do we do with all the data? For the stroke volumes are very interesting if you're doing shunt quantification. I've got this case from Michael, and this is a patient with an atrial septal defect. So in this patient, it has a hole in his atrial septum, and the blood flows from the left atrium, where there's higher pressure, to the right atrium, and then goes back into the pulmonary circulation. And you want to know how much flow is going through this shunt. And you can measure that by phase contrast MRI by measuring the stroke volume of the right and the left ventricle. So you're measuring the flow volume in the aorta and in the main pulmonary artery. And then you can calculate the differences between both stroke volumes. And as you can see here, there's almost four times as much blood flowing in the pulmonary system than in the systemic system. So this is a very relevant shunt. Normally it should be equal. You want to do these measurements accurately, so you need to avoid another error. That's the misangulation. In through-plane measurements, you're only measuring the flow that goes orthogonal through your measurement plane. If you misangulate the plane in the vessel, you're still measuring just the flow that goes orthogonal through the plane. But this means you miss the peak velocity. And we did this explicitly in a healthy volunteer. And you can see with a malangulation, you underestimate the peak velocity. And an angulation error of about 15% leads to 10% error of peak velocity and flow rate measurements. So you need to be careful. This is nothing you can adapt after you've done your measurement. You need to be careful when planning your measurement that you're really strictly orthogonal to the flow. Another thing you need to think about before doing the measurement is temporal and spatial resolution. If you're only measuring every second time point, you get an averaging and therefore an underestimation of peak velocity and flow. And it's the same for spatial resolution. If you're measuring very large voxels, then you're doing an average and you underestimate your peak flow. So these are recommendations from the German Society of CMR, and they recommend that the temporal resolution should be at least 45 milliseconds, and you need at least 4 to 6 voxels in your vessel to properly quantify the flow and velocity. So that's what stroke volume all about. Now we're going to flow volumes, regurgitant and fractions. And this is very important in valve insufficiencies. So here you can see the aortic valve, and in this healthy volunteer it really moves a lot. So for clinical application, if you want to measure the flow in the aortic valve, you need to follow the valve. There are special sequences for that. Unfortunately, we don't have them. So we plan at least 3 stacks over the aortic valve to get the right plane to measure the flow. And then you can see here in this patient with aortic insufficiency that the aortic valve isn't closing properly. So there's this triangle still open, and you can see the insufficiency jet going through this triangle, and you can quantify that. Peak velocity and peak pressure gradients are very interesting for stenosis quantification, not only valve stenosis, but also vessel stenoses. And to quantify these stenosis, you want to measure the peak velocity. But to measure the peak velocity, you first need to find the space where the peak velocity is. So there are different stenoses. The most common are the valvular stenoses, and you see the stenosis jet here. But there are also subvalvular stenosis, for example, in hypertrophic cardiomyopathy. And you can see the stenotic jet just beneath the aortic valve here. And what I find is very helpful is planning an in-plane flow measurement. So you're doing the same that we did before, planning a flow measurement, but you're not encoding the flow through plane, but in plane. And then you can find the place of the peak velocity. And that's where you can plan your through-plane measurements to actually measure the flow. You cannot measure the peak flow in the in-plane measurements because they are kind of thick and the flow jet is really thin. So you always should quantify the peak velocity in through-plane measurements. Now you see these funny-looking black dots in the white area. If you look at it really, it should mean that the white flow goes up, and there are some points where the flow goes down. That's not possible. So that's another error you need to avoid. That's called aliasing. And it has something to do with the ominous velocity encoding factor. The velocity encoding factor is the peak velocity you want to measure. And you're telling the scanner, this is the peak velocity I want to measure. In this case, 150 centimeters per second. And through adaptation of the amplitude and the duration of the bipolar gradients, the scanner sets everything so that the Wenck value will lead to a 180-degree phase shift. So with increasing phase shift, the scanner measures increasing velocity. And that's how it should look like in a very old 1.5 Tesla scanner. But what we did in the other measurement, with the in-plane measurement, there the Wenck was too low. And if you're setting the vein too low, with increasing phase shift, the velocity goes higher, but at 180 degree, the scanner, but if you're above 180 degree, the scanner thinks you're coming from 0 and going to minus 90 degree and not to 270. So the scanner doesn't realize that you're above 180. It thinks you've gone all the fast way to minus 90, and thus it makes this aliasing artifact, and it measures negative flow, although this would be positive. And this looks in a very intense version like this. So in the areas of peak flow, you get a color shift from black to white or white to black, and, which isn't logical. This is called aliasing. And you can correct it with software solutions, but you can also just check on the scanner and then adapt your VENC after the measurement. So the logical solution would be to set the VENC very, very high, so you cannot get any aliasing at all. If we're doing that, the problem is there's a lot of noise and you're not measuring right. So the peak velocity is overestimated. And you don't want to have that noise, and you want to be very sensitive to slow flow and all the, in your scan field. So you should adapt the VENC to 10 to 20% above your expected peak velocity, and then you can check whether you have aliasing or not, and if needed, adapt the VENC again. So all this flow quantification is very interesting in clinical routine for congenital heart disease. It gets more interesting for valvular heart disease and for vessel stenosis. And especially congenital heart disease is really complex, and you want to do a lot of measurement planes, and it's really time consuming, the prescription of all those planes. So you might think about doing a 4D flow MRI scan. How does that work? So in the beginning, it's all the same. You collect data for one time point, for the reference value, and for the flow-sensitive direction, here in this case, feet to head. But you're not, so this is what we did all the time. This is single direction just through the plane. If you're adding flow sensitivity to the other directions, so right to left and anterior to posterior, so you see that here, right to left in the right pulmonary artery and anterior to posterior in the main pulmonary artery. Then you get still a 2D scan, but it's 3-directional. So you're measuring 3 directions, and you cannot have those angulation errors I've talked about earlier. And if you're adding a lot of more planes, then you're going from 2D to 3D. So it's 3D scan, it's time resolved, and it's 3-directional. And that's what 4D flow is all about. So, and then it's all the same with it, as with the 2D flow. You collect your data over several time, for each time interval over several cardiac cycles. And then you calculate your phase difference images and your magnitude images. And since we cannot do a lot with the black and white images with the 3 velocity encoding stuff, we have post-processing software to look at the 4D flow MRI data. And here you can see a healthy aorta with sinus vortices in the aortic bulb, the central ejection jet, and you can measure the flow at every plane in the aorta. In contrast, in this patient with a bicuspid aortic valve, remember it's 1 in 100 people having such a bicuspid aortic valve, you see the eccentric ejection jet that hits the outer curvature during systole, and with large helical flow developing in the ascending aorta. And these patients often develop aneurysms in the ascending aorta. And well, you could think if the jet impacts on the outer curvature, that might lead to aneurysm formation. But this is just looking at the data. We can also quantify it. So there's this great work where they measured the wall shear stress. Wall shear stress is the force that acts by the flowing blood on the endothelial cells. And this changes their physiology, and apparently in regions with elevated wall shear stress, They are fragmented elastic fibers, in contrast to the same patient, but just on the other side of the ascending aorta, with normal wall shear stress, where the fibers were not fragmented and looked very much healthy. So with 4D flow MRI and measuring wall shear stress, you can see that this has a big impact on the development of aneurysm formation. You can also measure turbulent kinetic energy with 4D flow MRI. That's the energy that gets lost for blood propulsion and is just turbulent and doesn't help the blood flowing through the aorta. And you can also measure pressure differences, for example, in vessel stenosis, such as aortic coarctation. Remember, it's not the actual pressure you're measuring, it's the pressure differences you're measuring with 4D flow or 2D flow MRI. And the best thing about 4D flow MRI, you can measure congenital heart disease very quickly in just one scan, and then go to the scan and evaluate all the relevant contours you need for understanding the case. So to conclude, phase contrast MRI is a powerful technique for flow imaging, and it has clinically relevant applications. So it's great, and I thank you very much.